Just to give what I like about what I'm doing is, and I hope this motivates you too, is that we are talking here about data communication, for example, but we also really do this. So, for example, it's a sunny day, so it's about 3 years ago. This is something we did in 2019, 2020. This is something you can check. We are doing real data links. So this was the first time we were transmitting. This is the outside of the Fraunhofer where I'm working. And this is a data experiment for the first time to go over relatively wide times for 1 kilometer with a decent amount of data. So this is a transmission of 56 gigabit. We later did also a bit higher, more than 100 gigabit. In the sense that I have to share this also on Teams. In the sense that we are trying to motivate really what we are doing. So it's not just theory or just ideas, but it's something we're really building. And what you can guess from this is a backhaul thing. So this is an antenna. This is a system we built. And this was then transmitted to one of these buildings over here. And what I want to give you in this, at the time it was not a world record, but presently data transmission at about beyond 100 gigabit per second over the air. So that's a very nice number. Is it getting you into the range of world records? So that gives you a flavor. So you can compare to what you have today in your hands. Is in the range of tenth of megabit for the transmission, but this is really cool because we are essentially predicting what's going to happen maybe in 2030 or so, when also something like that will become available. So it's the first, some of the first. So it's really, you see that it's a dish. It's a point of point-to-point connection where there's no trees. The trees are just somehow in the way, but not really blocking it, so you can get a feeling how things are running. And then the point about the engineering we do is really build it to the point that it really works. So that's something I would like to tell you. And today I would like to give you a little bit of flavor for what is really happening in the sense of frequencies and how do we do this. So what do you need to know? Just a second. This was changed. Need to update this. So the lecture today will deal with how we would approach this, something like that. We are transmitting this vast amount of data, and we are trying to understand what is needed there and what are the difficulties. So let's go to so last time, just a second, sorry. I closed it. Last time we learned a lot of things on the item of how to get from basic theory from the Maxwell equation, and some things I hope you didn't see before. So that was what is new is that for the first time I hope we do guided wave propagation. So that was the idea. We take a cable, we take a waveguide, whatever a waveguide is, and we learn to transport information waves derived from the Maxwell equation. So that's something you can really tell. And the reason why I did all this is that when you're approaching a system, you would look more into hardware. So when you are learning the kind of hardware we have on top there, this looks like something real. This looks like a component on the right side, which is already integrated. Yeah. And for example, what you see here is a chip integrated, or this is the detail of the chip, and that then will be part of a module, which again needs integration to finally arrive to the antenna, which I showed you with the transmission link. Yeah, so there's a couple of, there's a couple of instances where we are going down from a system level to a subsystem, into packaged components, into components, and then down to the wave level. That's what you, and that is what you approach here. And one thing we learned was, what is something which we can now derive, is that we are now not just sending currents and voltages through something like what we do with a normal cable, but that we define structures in 2D, later in 3D, to guide. This is wave guide, it's guiding wave. It's not conducting currents and voltages. There are voltage and currents, of course, you can calculate those, but essentially what you're learning is you by putting different metals on top of a dielectric, you are guiding waves through something. Yeah? And it's obvious that it's not only a story of connecting materials, but you also see, as I showed last time, the brown is gold and the yellow is also gold in different fashions. So we have to think a little bit about what the waveguide and the properties of the waveguide would do to the wave. Yeah? So that's one thing which I wanted to show you. There was this idea that what you learned before, that a wave is something like which has essentially a TEM idea, yeah? So that you have E and H, the field vectors of electric and magnetic field, are still there. However, because you put them into something, which is in this case a piece of dielectric, a plastic or so, and then topped by something which is there, that you can now decide where the wave goes. That was one idea, and the formulation was that actually when you try to imagine the fields, they are still TEM, but they might look a bit differently. So it's not just this classical thing like in a planar wave. The concept is the same, but it will be will look a little bit different, but will essentially transport power, information along this path. That's something which you can learn. There were a couple of, and the description was that from both sides, looking from a cable, you take a cable and try to guide it through a cable. Then it's clear you just go along the cable, but you can much more generalize this, yeah. And you can take it from this simple cable description that you essentially make a wave description as a function of space and frequency, and time especially, and then you get something which looks like a wave. It's an amplitude times a decay constant over space times the time the part which is part of the time. And then these items can also be related to a very generalized description of something which still looks like a circuit. Yeah, so we can, the relevant factors you have in this, they can be directly attributed to more generalized descriptions of R, C, and L, which you still have in your mind like components. Yeah? So that is probably something which you can relate. And then you can also nail them down to something which is meaningful, for example, an attenuation factor, or in time, the beta is the phase factor. So that's something. And as we learned also from this story was that whatever you have there, whether it's nothing, space, empty, or whether it's something dielectric or something which is filled, that you can relate that to an impedance. So the concept, the generalized concept of impedance works for the transmission. Yeah? And then what you can actually get then is even circuit parameters G, C, L, and R in a generalized way per length that you can also understand them from a circuit. It's the same story written from different sides. Yeah? And then we even put some loss mechanisms. I don't want to go through the details. The only thing which I would like to mention is what is really relevant in a circuit. So what is really critical is the metal losses. So when you have a bad metal, you take cheap metal, then you will consider relatively strong losses. So if you just don't take copper or don't take gold, you will end up with relatively significant losses. There's the loss tangent, which is the dielectric part in this. So just to go back, so if you charge and recharge things, that is a lossy mechanism because you're sending the wave through the dipoles. And this is also interesting because you can make cheap metal, cheap plastics, which are really non-conducting and have very low attenuation. But if they're, for example, polluted with something which is conducting, cheap plastics can also be really damping. So that's something which is interesting. For example, when you, just one idea, people are thinking today in recycling. So, and we had a radar which was transmitting through a bumper in the car. So you had a bumper, and this bumper thing, which is a relatively cheap plastic, was produced by multiple producers, and they all had the same specs, but they didn't have the spec for the radar. In one case, because the material was pure, the radar waves would go through, while in the other case, when they were using the second supplier, they had recycled material which had some kind of conductivity in it, so the wave was heavily attenuated. So it's not a physics type of problem, it's a real world thing that you have to match your materials and understand them all, because it's also things like radar and communication, as you know, are omnipresent and more or less cheap. So this is not something where you spend thousands of dollars on. A radar chip goes down to a couple of dollars today, so that's just to give you a flavor. So this is real world. And then there was also the frequency thing, so just as some ideas. So the metal conduction is square root of F, and the dielectric losses, that's the easiest thing. Capacitor, when you increase the frequency, the losses in the dielectric losses go by F, because for every charge and recharge you do, you lose something. So the higher the frequency you go, the more lossy it is. And the last thing, which is covered there in relatively interesting equations, is that you have also a skin effect. So the idea is you have something, and then you increase the frequency, and in both metals, especially in metals, the conduction goes to the skin, because the fields in the conductor are pushing themselves outside to the corners of the metal, for example. So effectively, you're reducing the cross section of the conductor, and then some things like roughness, and this is always good to indicate that it is real. So you plate different golds, and you're very nice in processing, but you still see already from the optic limit that something which is plated gold, which is the brown one, has a different surface structure as the same pure gold, which is sputtered, so which is much more flat. So you see these things start to matter. So it's not just like easy things, but for more complex structures, you have to consider those. That maybe helps you in understanding a bit how we function. Okay, and the only fantasy you need at this very moment is that you are not going to look at a simple cable. So that's something. So the future of the 21st century is that anything that we do is particularly integrated in 3D. So when you just think of, for example, a chip, in CMOS today you have the transistors on the low side. Because of the losses, all the conduction we do in RF go to the high side, we go to the top. So what you have to think is to migrate the signals from here to here, transfer them, and then get them back to some other transistor down there. So this is where you're starting to think, okay, doesn't seem to be so simple, and you understand that any of these items needs to be described in a way that we can take it. So it's also not an easy structure. That's maybe something which also helps you. And with any generation, for example, of your cell phone, this structuring gets more complex. So if you look at how the chips looked like for early iPhones and now what we have today, the only thing which is common, it's getting more complex. So that's why this leveling of the description, that's what is interesting to me. You have some description which is valid for something. Maybe for a cable, you can use the same description for something more complex. The actual data will be more complex. You need to do that, and you need to do it precise. But the idea is always the same. So then you can get an abstraction level. And also this idea that you have a chip with bond wires, you know that for example, if you take your cell phone, cut it in halves, you will not see wires anymore. This is outdated. Yeah? So this is something just for maybe for analysis or for, but we have a highly integrated scheme today, also for all those chips which are packaged there. This is what you have to learn about, because otherwise we can't build these systems. So now, and the question is now how to approach any of these single-ended components. Yeah, so we just take any of these pieces and cut them into something which we want to deal with. Yeah? And there's a principal idea that we just, whatever we model, we put it into those fundamental ideas. We say there's something serial and there's something parallel, which is a serial inductor and a parallel capacitor, because we always, it's like a cable to ground. And then we have the related loss mechanism, which are both for the serial. I mentioned the metals, which per length are simply non-conducting or have a resistance. They make losses. This is an easy way to understand them. There are more, but this is one of the mainstays. And the second thing is there's a parallel loss, simply because you charge anything which is around you all the time when you go through that. Yeah? And what we are trying to understand now is that how to get all these components in a row. Yeah? And the way you take is that through this system, in the first approximation, you say the component does something, and then at the end, there's also something happening when you go to the next component. Yeah? In the complicated case, this is not fully true, because if you take the same component and it has a different environment, then you may have to check for some of the things you assumed. So, but it's a first guess. It's a bit iterative what we are doing, but it's a very good guess how to deal with these things. Yeah. So, for example, you could say if you have this transition, for example, here, this is different from this one because this one has two neighbors. This just has one, but it's you're getting there. That's one idea. Yeah? So, and now what you're doing then, and this circuit which you have there is quite fundamental. So this is a description, but it could be anything we have in this room, as long as it's part of the part we want to check. Yeah? So, and then the trick is here that you relate that component to when it hits the next component. Yeah? Or even free space, which is the same as the next component. And then we take something which is different from what you normally do. You're looking at the situation, in this case, from the extremes. And you could ask, now, why is the guy telling me this? I'm not interested. But you have to think practically. So the idea, for example, when you have a loudspeaker here, or it's just something which we are connecting, for example, take something which does not affect me. So we take, for example, this connector, yeah? And we need to know what it's doing when we are just having it as it is. It's not connected. Yeah? This is a real situation for us. So it's not something I invented. The possibility that this thing does something when it's not connected is real. It's not something which you haven't seen before. Yeah? The same thing is when it's maybe short circuit. So for example, we put it through some metal that might be somewhere unlikely, but it's still a possibility. Yeah? And this is new. Why to take it from the extremes? And the reason why we do this is because simply it happens. Yeah? So the design we do is always taken not from the ideal case, that everything is well and smooth and fine, but for example, when you think, for example, of antenna, you are interested what it does when it transmits, but if there's something flying into the path, or you're running by something, for example, if the cell phone didn't work when I'm going along something which is fully metal, for example, here I could have the cell phone here, I'm passing here something which is metal, so I cannot really say this doesn't happen. It's a different perspective which I'm transporting to you. Yeah? And when you think these states from the idea what is really happening there, it's interesting. Yeah. So, for example, What would happen with an open cable when you have this again? What would be your answer? What does this cable do when we do nothing, when we're not connecting it? What would be your idea? What does it do then? What could it do potentially? Do it this way. There's two things. If it's a wave, there's a wave traveling. What could the wave do? Yeah. So this is the most likely case, and this is nearly always true. It reflects, because what is around the conductor is not conductive. What is the other theoretical possibility? What could this also do? Yeah. And the surprising thing is many people say that. It's also, of course, very theoretically very true, but the conditions are not always met. So when you, for example, check what a normal open coaxial cable does when you just have it open, it's mostly reflected. So there's not, to make it really an antenna-like, that you have to hit certain conditions that it's really radiating like an antenna. It needs a directivity, as we will learn later, but normal connectors don't have that. There will always be something, it will be suppressed, but you can see that. For example, if I keep a very sensitive receiver here, I will see something, but it typically will not happen. And the point is also, obviously, these points are not really unreal. And because of that, we are just changing gears here. So the first thing is that whatever happens there is not really bound to the description. So we can look at it from an impedance perspective, and because sometimes we are lazy as engineers in the calculations, we also do the same thing and turn it around and call it admittance. It's just a matter of taste. Having computer programs, this doesn't really matter, but sometimes for looking at it, it's easier to sometimes to check in impedances and admittances and think in them, because simply the calculations go easier. I will explain that in a minute. And what we are now doing is, instead of just talking about waves, we are going back to a very different way of looking at the system. So we are going away from saying this is a current and a voltage. We are just typically looking at power, which is reflected and transmitted. Yeah? And if it's like that, then you can express the whole story pretty much through a reflection coefficient, apart from what's happening. So impedance is nice, you can say there's an impedance and so on, but you can also simply say you reflect something. And if it's not reflected, it's transmitted, and then you get a good feeling what the system really does. So the description can change, but not because it's crazy, but because it's simpler to really to appreciate what is happening. So what we say is, at the end of the day, instead of looking at the impedance change and start to go electrical, we simply say, when something leaves something, it can either be reflected or transmitted. And that helps us to understand the system, because we can multiply ourselves through the system and we will at the end know what it's doing overall. So we have some couple of definitions, and the only things which you have to remember from this is that we can talk about currents and voltages. We don't like that for a very simple reason, because any current or voltage description will be strongly impedance dependent. That's what this first equation says. And the impedance itself of the thing we are looking at is strongly geometry dependent. So all the time when you meet something which changes the geometry, then you have a very different system you are in. In a waveguide, it's a bit simpler. When you're in a cable, you have a constant impedance. That is a part of the cable, for example, as we saw last time. And then it's easier to understand, but overall you just want to go through the system and see how the power and the energy flow. And that's why we go to this. And there's a reason why there is this description. So you can have this complex impedance, which is just a number derived from currents and voltages. And this, in a way, this impedance is related to this reflection coefficient by this formula. So these two are really important. Yeah? And because of that, because this is a mathematical transformation from reflection to the impedance, we also later looking at a specific diagram, because when you plot this in a way, this transformation, you can suddenly see things very easily. That's the mathematical background. Yeah? So coming from a very practical idea that you have something which is describable, yeah? You're coming to a mathematical form, and then you say, okay, let's go to this, come to this idea of reflections, and then let's use that for analysis. Yeah.
What's even
That is, you caught me already. This is something I anticipated. The idea is always, when you have something, a box, we have a convention that everything which goes to the box is A, and everything which leaves is B. Yeah? So you see here the reflection coefficient is the incoming wave is A, and the leaving wave is B. This is a bit anticipated, we'll see that. Yeah?
But for example, if we have this cable with nothing connected to it, A would be the wave going inside, and when everything is reflected, B would be zero.
No, we do it differently. That's a good point. But what you say is, you have a freestanding cable, and then you take a bit of a test signal, assuming that it's a small amount of power you put in, and then you sense the reaction. That's how we look at components. Yeah? So you put them in whatever configuration, and you assume you slightly excite them. And then something happens, and this is what you detect. In a passive way, it's very simple, so you just put a little bit of power and you get some kind of behavior. Yeah? The trick why we are doing this is very simple, because the process we just described over frequency is easily done. So you say, I'm exciting at this frequency, and I know what it's doing at this frequency. Very simple. Yeah? And you can get a very easy formulation for what you are applying to do. And this is now the graphical representation of what we just said. And first of all, forget all the numbers. What we are just looking at is very simple. So you just look at this from the idea of reflection. Yeah? So you are in the center of this circle, and you say, okay, I'm sending out I'm in my component, I'm exciting it, and what can happen? If there's no reflection, nothing happens. So the wave is fully going into the component and is fully transmitted. Yeah? In case there is reflection, a little bit of this reflection, so the radius is this. Yeah? So there can be total reflection along this line to here, this is 1, or a part of the reflection. A little bit is reflected when we change, so, and the rest goes through. And what we need, however, is we need a phase term, which is important for wave, because you can have the same, because this is something I didn't say yet, I have to check that. When we have an open cable, what do we expect? We expect total reflection, because if it's not really transferred, the energy has to go back. Yeah? Now we are short circuiting it. What will happen with the power again? So you have a cable and you make a short circuit like this. What will happen to the power? Again. Yeah, but this is a bit crazy. You have the extreme situations and they're doing the same. Does that make sense? No. What is the difference? You cannot have water and fire at the same time and say water is fire. That doesn't make sense. what is similar, that's where you're correct. In both cases, you have total reflection, but they have a different phase. Yeah? And that's easy because here, if you ever saw this, if your physics teacher ever did that, you can play this game when you have two parallel lines, you have an open, then at the end of these two cables, the voltage is maximum, and if you have a short circuit with some cable laying over, the current is maximum, which is a difference. Yeah? So you cannot either voltage is high or current is high, both cannot be. Yeah? So this is, I think, if you have ever seen this experiment, maybe for those, just put it on the wall. So what the physics teacher might have done, there's a second chalk here. Didn't bring a foil for that. Chalk. Where? Ah, thank you. Ah. So what your physics teacher might have done, you have two cables, and the wave is traveling along this. Yeah? And now, if it's open, then there will be a voltage maximum here. If you, how do you see it? And then you can do the opposite. You do the same thing, and you put a piece of metal with maybe with a bulb here. Yeah? And you see, in this case, there's no current flowing, and in this case, there's of course current flowing seen by the light. And what is the difference? The energy will both be reflected in both cases, but in this case, there will be, let me just check, this is an open, there will be phase 0, and in this case, there will be a reflection with a phase added, which is 180 for the power. Go ahead.
I can't find the English word, but isn't the second case that the energy is consumed by the...
Yeah, that's a bit, this is why I hesitated.
Okay.
The idea is, okay. In this case, you can, question is, what does the light do? You can say there's current flowing, and the light can be an indication that there's really some current flowing. Okay. That is one way. You could also, it has to do with something I'm going to say later, but it's just like, in this case, there's no current, and in this case, I is max. And voltage is, in this case, is 0. Yeah? And this is, and these are obviously not the same things. Yeah? So this is a totally contradictory thing, although from a power perspective, the situation is very easy because in both cases the power goes back in this very simple case. Yeah? And now what is the difference? The difference is that in this case a phase is added. So fire and water are still different. And this is also a good example, based on the discussion we just had, why this concept is useful. Because at the end of the day, it doesn't really matter. You only have to describe it well. And it's easier just to say what is happening rather than start talking about the detailed physics of the voltage and current. It's a practical means. So, and what you do then is just from the reflection, you just look at this diagram. Whatever happens, so we say if we have the open case, this is here, then we have phase 0 for this reflection. Yeah, so if we have a total reflection, we put it here, it's a phase 0, and you turn it around, whatever can happen. The other case, this is the short, where you say on the left side, you say you get an added phase. Yeah? And these are just very simple extremes. And the question is now, as anything can happen, so there could be, as you say, there could be, for example, also something which is not a short circuit, but some resistance. That's what you implied when you say there's something loaded, which has a definite resistance. So in this case, you can say there's then a resistance here. So this is not a short, but a finite resistance, and that means that also the amplitude can change. So it's a good discussion we're having. It helps you a little bit to get into it. Yeah? And the only fantasy you need at this very moment is that depending whether you're going away from the extremes, that you say there can be other situations. Open is infinity in impedance, this is 0. Yeah? There might also be whatever, 100 ohms or something in between. Yeah? And this is why we are now introducing this secondary diagram, which is essentially the mathematical or the graphical formulation of this transformation. This is something which is not obvious, but it's a special transformation which goes between impedance and this reflection coefficient. Yeah? And then, because it's not a linear description, the simple diagram which we had before, so it's just a normal polar diagram with phase and a reflection coefficient, a number between 0 and 1. This now transforms into non-straight lines. Yeah? And what is also plotted in this diagram in the overlay is the actual impedances in ohms, and it has a real number and an imaginary number. That sounds dodgy, but some of this diagram you know already, so let me take the simple approach. What if we have a cable and we connect it to the same cable? What would you expect? Quite trivial. Nothing. Yeah? So whatever the impedance of the cable is, it will stay in the center and has no reflection. Full transmission. Yeah? You connect cables, no problem. What if the impedance of the next cable was, let's say, we take 100 ohms and we have 200 ohms for the next cable? There would be some kind of reflection. We don't know yet in which direction the phase goes. Would it go up or down? We wouldn't know. But what we would definitely know is because it's a real number, we can say it's either going to be 180 or 0. We don't expect that something strange changes, and so that we get 45 degrees or something. That would not happen if we have a real cable. And if you ever did something like Leistungsanpassung in a real system, so you're just connecting a resistor to a resistor, you're coming exactly to that conclusion also mathematically. Yeah? The point is now why we need the rest of the diagram is simply there could be anything. So for example, there could be now something. So if this has a certain impedance and it's connected to something which is not real. Yeah, and let me explain why I'm talking about complex numbers here at all. That is very simple, because if we go back to this thing, we just learned that any transmission line is described by something which is non-ohmic. It's described by L's and C's. Yeah? It's a finding, and it requires you to go to this description, but once you have accepted that, you have already done everything. There's also a benefit. It's not only a complexity. Yeah? And you could now sue Faraday or whatever for describing it in such a way. But the point I'm trying to make is only that we learn that a cable, when it's running forward, it has a serial inductance. This is relatively simple. And a parallel capacitor is always there if you have two metal plates, which is this part. Yeah? So that means anything which we can encounter beyond the box, that's the thinking, could have an impedance which is not real, because it involves capacitors and it involves inductors in this description. That's why you need to think about that. Yeah? So there can be an arbitrary phase change. Yeah, anything can be encountered. And the reason is now why to look at that is very simple, because with this diagram, we can cover all situations in a single diagram. That is the beauty. So it doesn't look so well when you think of it for the first time. You say, I don't like it. I didn't like it either. But there's something positive here, is that from an impedance description, admittance also the same, we have the extremes. Yeah, unfortunately, a not connected cable has the impedance infinity. Yeah, so what you have here, this, if there's no transition, there's simply, you need the extremes. And you cannot avoid that somebody short circuits this thing. Yeah? So that's the same idea. Yeah? So you will have the case that total reflection is possible. You cannot say it doesn't happen. And what would happen then if you had to do this in a Cartesian diagram or in something which is planar and not so and linear especially? The interesting cases would be somewhere beyond the door and beyond the window. So that is not really helpful. Yeah? So you're transforming something by this transformation to a circle. I don't say it's obvious, but I'm saying it's useful. Yeah? And why now this description? Because when you now look at real structures, you simply encounter all these situations. Yeah. So here I would say you are not convinced. I don't need this. But when you go to something real, what you have to build in the end, you're coming to the conclusion that we need all kinds of geometries which we have to master. Yeah, so for example here, this is an amplifier which you are, for example, using for your cell phone. This is where your data go through when the base stations are connected. And so what is it? So it's something which as an input here sends the data through various stages and then reconnects them again to form hopefully a fully amplified signal which is otherwise unchanged. Yeah? And already because we need to go through these structures, because we, for example, a requirement which forces us through these structures is you simply want a certain output power. Yeah? So you need a number of transistors to generate that in the final stage, which have a certain size, and you simply have to get the energy together again and to combine them and finally to come out again. Yeah? So this idea, I don't encounter this situation, doesn't really jive. You will face all kinds of trouble and you need to be prepared for that. So that's what this thing does. So what you do is the component, you're starting here with maybe with a 50 ohm impedance at the input, and then you will go through the system. Let's go to this path here, and at every point when something changes, you will have to be asking this question again. Yeah? You will not necessarily look at this diagram all the time, but you will make calculations which tell you so much is reflected, so much is transmitted, and if you're doing well at the frequency of interest, everything goes well. So you're ending up with the signal at the end of the day. That's why we need this. Yeah? Before we go now understanding what I just said in geometry, there's also maybe a little bit of thinking needed. So because we are dealing with waves. Yeah? So maybe we also have a structural insight where we are. So what we learned last time is that the product of wavelength and frequency is the speed of light. Yeah? And as long as we have a decent, this is true, as long as we have a decent damping, and why is it useful to talk about that at all? Because we would not build this on a strongly damping material system. So if the wave would not be able to transpire through that structure here, then you wouldn't look at it, because we can describe it, but it's not really useful. So for example, if you exclude the active part and just talk about the passive idea, you would expect that the structure, the wave can go through the structure. And then at certain point, it's even amplified, like here and here. So in the end, you even get a benefit. You get a higher signal rather than a lower one. Yeah? But the modification here in this case on the ratio between wavelength and frequency is just that there's a change in the wavelength. And this change in the wavelength is defined by the index of refraction. And this is important now. When you look at this, what is modified? I asked the question already last time. That is, Deutsche Telekom buys frequencies, so wavelength is modified. And wavelength is modified by the index of refraction or by the square root of the epsilon. You will see in a minute why. So inside the material, the waves will be shorter. That helps. That's nature, but it helps because the things we have to build are getting smaller. Yeah? So because we will see later that we will use these structures in relation to the wavelength. And if you are inside a dielectric, the problem, the wavelengths you have to deal with are smaller than they are in free space. So I have my cell phone, which has 10 centimeters length. And if I'm going inside the plastic, modifying the epsilon by maybe the index of refraction will be 4, so the wavelengths will just collapse. So the things I have to deal with are smaller inside the material than in vacuum. Yeah? And also the impedances, which we get for free space, they are 377 ohms. That is 120 pi. This is what free space is giving us. And anything inside the materials is getting low. Yeah, and why is that? Because the impedance inside the material is modified by the square root of the permeability by the permittivity. The permeability is typically 1. So that means the impedances is changed by the square root of the epsilon. Very simple. So it goes down. Yeah? And that answers also some of the questions why, for example, if we make a tour to MediaMarkt and you look at the cables you are getting, they're in the range 50, 75, 100 ohms. That is the answer. So it is simply the epsilon of the materials used, which that's why when you bought your first satellite transceiver, if you ever did, or your first cable, you were getting these particular impedances sold. Yeah? So that's the simple idea. So which wavelengths are we at all? That's also very important. So first of all, let's take it from the frequencies because these are unique. Yeah, so first of all, what is the range of the spectrum where we are with the microwaves and the millimeter waves? That is somewhere from 10 kilohertz to 1 terahertz. So gigahertz is in the center, and 1 terahertz is 1,000 gigahertz. And the typical things are updated this. We today are with the simple mobile communication. You have so far been roughly 500 megahertz on the low side. In Germany, it's a bit higher, to 2.7 gigahertz. That's all the stuff you're presently mostly using. That's already 2.2 gigahertz from 500 to 2.7. Yeah? Then we talked already, we have some things like microwave cooking. There are some bands excluded, which we don't use. They're done for medical and environmentals. Also WLAN is there. And then there's also some band in between, especially which is 5G today. So this is same frequencies, but a little bit higher. And then there's also, this is a bit strange here, a bit also unusual, that for some frequencies there's a coexistence between mobile communication and WLAN. Sometimes they cooperate, and that's a specialty of 5G. They use the same frequencies sometimes. And coming to the wavelength, so you see here, for example, that at 3 meters is 100 megahertz, so that means that 3 gigahertz, so roughly this here, this is 10 centimeters. 10 centimeters is decimeter wave, it's 3 gigahertz. 30 gigahertz is 1 centimeter, just in free space. And then which ones are we using? This is also a bit of an update. So what have you seen today? What has your body been hit by? Most likely. So there's the mobile communication. This is in Germany mostly 900 megahertz and 1.8. And then there's always adjacent, there's radar bands. So for communication, we use certain bands. And then because at low frequencies, the free space propagation is good. So for example, the air radar, which is used to make you to safeguard you, this is typically L band. So this is around 1.4 gigahertz, where you look to Amsterdam to check for the flights, for example. This is what you see when you see a radar section for an airframe. And then there are some other frequencies which you're already using. If you're getting broadcast for your TV, then it's around 11 gigahertz from the satellite. That's SATCOM. Yeah, so that's what we're effectively using because it has such a high bandwidth. So when you're watching, if you're not using internet TV but broadcast TV, which we call from the satellite, you get it around 11 gigahertz. You can check this information on your TV, what is coming in. Yeah, so that's probably the highest, and then the other ones are also coming up, and most prominently is now the new links you will get for your phones, which is around 26, 27, 28 gigahertz. For these very new 5G phones, they already can do that. With these, you can get a lot of bandwidth, so you can get maybe a gigabit per second already to your phone. So that's quite remarkable. They're not widespread. I also don't have anyone, but this is this band, which is it's reality today. So in certain hotspots in the city, at stations or at airports, you already get that. Yeah. So and then it flavors down, and we have already for 6G. We are already talking about higher frequencies because there's unused band which can be used for very high data rates. That's what we are researching. For example, the one which I showed you in the beginning, this was actually at the edge of this at 230 gigahertz. So really high. And because the damping in the atmosphere is then very strong, I'm always showing you this at sunny weather. So this, for example, works at sunny weather. At 1 kilometer, if it's raining, it doesn't really work, because then the attenuation is getting so strong that this link degrades. It still works, but it's degrading. So it gives you a flavor where we are with the wavelengths. And what you can use today already is up to about, there are some satellites which go to about 800 gigahertz. This is roughly what we can do today. And this is mostly used for atmospheric research. So we're looking at some, this is very high. And the reason why we don't use these higher frequencies is simply there's not yet any active components which give us amplification. Yeah? So because we have losses, we need something to amplify, and especially in this region here, 300 to 800, there's simply nothing yet which is good. Our specialty at where I work is that we can cover these bands already, but there's few who can really actually do that. And now comes the idea of how we look at that. So when we want this very different way of looking at this, we always do the same thing. So no matter which frequency we look at, we have a special device, a network analysis, which does what you asked for, excite and reflect. It measures this at a very low frequency, and in between there's only an up converter. So maybe where's the setup? It's not in here, but just to show you how we do this in principle, we have always the same receiver type, and then we just put the multipliers in between to go to the very different frequencies. So it's always the same system, exciting at the different frequencies, and then only this part changes. But the principal part, which does the data analysis, this is shown to the right, is always the same. So that's why we were a bit lazy in thinking, so that's why we do this. maybe explaining why we are not doing this differently. So one idea, when you have a link, why are we not looking at the bits when we are looking at the at a link? We are looking at the bits, but only if they're down converted. So we put data in, and it's a transparent channel, and we get the data out again. Why? Why don't we? And this is a very simple thing. Why are we not just sending broadband signals into the air? So, for example, we take a 40 gigabit signal and just radiate directly into this room. What would happen with the signal?
The range of the signal reduces. The range of the signal reduces.
Yeah, that will happen anyway. But what is the problem of something like that? So of a directly modulated bit. What is the problem? So how does this look like in the spectrum when you make the analysis of such a signal?
Infinitely many frequencies.
Mm-hmm. And how do many frequencies go about in a room like that?
I would say the antenna has specific characteristic to only transmit certain frequencies.
Good.
So from this signal, only a few frequencies will be transmitted.
Yeah. So that's very good thinking. So the idea is antenna is typically something resonant in some way. So it excludes and favors certain frequencies because it's a geometry. Yeah. Same for this room. Yeah. And the problem is that when you send something over a channel and you have very different frequencies making this up, we will come about the Fourier transformation in a minute. But the trouble is, you want the signal to back, so you need the different ratios of the frequency components to be constant. Yeah? And if, for example, let's assume this is a 40 gigabit signal, and so it has 40 gigahertz in it, but also 80 and 120. So assuming that you're looking at these three frequencies only, which is a simplification, some of this part will propagate differently than other parts in this room. So when they meet somewhere in the edge, they will be out of phase and it will not be the same signal anymore. So you lose the information. Yeah? So that's why we are typically, when we are going into free space, we are refraining to a certain frequency space or relatively small space and just modulate around the signal, so anything which arrives somewhere is more or less the same still. That's the idea. It's a fundamental idea. And here this is for example how we could look at this. So you can look at it from the frequency space, so that has multiple frequencies. There is no preference whether you do it in the time domain or in the frequency domain, but to look at it in the frequency domain is in this case much simpler. Yeah? Because this idea of sending all these frequencies in free space doesn't make sense. You learn they will never arrive, so you stay at one frequency and modulate slightly around them. Yeah? So that the frequency response of anything you encounter will be similar to any of the other frequencies you send. That's a very fundamental idea of a channel. Yeah? And there's no preference because you can all the time you can send back and forth. You can always transform them back and forth, but it's a concept to analyze. That's what I'm putting on you. Yeah? It's much simpler to analyze this in the frequency domain than in the time domain. For this. And this is, for example, here, and what I just meant earlier. So, for example, this is the channel we are sending. So, for example, this is here a radio signal at 2.17 gigahertz, so classical 3G or 4G signal. Yeah, and the center is 2.17 gigahertz. Around that, there's a small modulation because you need the bandwidth for the information. which is relatively 5 megahertz, or today for advanced mobile com it's maybe 100 megahertz, but it's not more. So 100 megahertz over 2 gigahertz is only 1 over 20. So that's everything which, so this edge of the signal will transpire in the same way as this edge. That's why free space propagation works. Yeah? And then, yeah, just as an idea. And the idea is then when we then starting to enter materials again, which is, for example, what we do when we receive and put it into circuits, for example, for amplification, we do the same. So we are entering a certain domain for the frequency, and then for the channel part, for example, we want amplification. So, for example, if this is a 30 gigahertz amplifier, again for the backbone, 30 gigahertz goes in and is amplified, or also 28 or 32, but 10 gigahertz will be totally rejected by the amplifier, will not be amplified. So there's filtering done all the time so that the components are specific. And what is now, and that is also something which we now learn, is that that the structures we see here, they have something to do now with the wavelength. Yeah, so for example, when we are looking at memory, the size of the transistors, we see this in this lecture, they are more much in the micrometer or even in the nanometer regime. Yeah? While the structures we have on those circuits which have filter ideas in them, they need to be about the size of the wavelengths inside the material. Yeah, so for example, if this is 30 gigahertz, I said this earlier, free space wavelength is about a centimeter, modified by the square root of the epsilon, which is about 12 in this case. Square root of that is about a factor of, let's say, 3.5. So 1 centimeter by 3.5 is something like a couple of millimeters. Yeah, and the circuit also is in the range of a couple of millimeters by a couple of millimeters. Yeah? Because all these structures which we use here are in relation to the are used in the relation to the wavelength, because that makes them functional. Yeah? That is a very principal idea here. So these connections which you see here are also in a way filter structures, and they need sizes which are in relation to the wavelength. That is new. Before it was just a cable. Here, this is now a filter. It's a resonator. Yeah? In many of the structures, that's why these circuits, that's why, for example, with RF circuits, you can always see them. Yeah? You see really the structures visible. Yeah? If there were nanometers, you wouldn't actually recognize anything. Coming again a bit to this transformation for this diagram. So that's what I said earlier when we would do this in a not in this crazy diagram which I just explained to you, but in this Cartesian diagram. The interesting thing was, if we would plot the impedances in a Cartesian diagram, x and y, then the interesting reflections would be beyond our reach, because infinity is far away. Yeah? And 0 is also far away. And you cannot really tell something, don't disconnect the cable. That doesn't really make sense. So they had to invent something which was putting infinity to a real number. And that's what happens here. Yeah? So you put it polar. And so the Cartesian diagram here, you see that it's actually bending. Yeah? So especially so this is the real axis here. And this is also the real axis. This stays. Yeah? But you see anything which deviates from the real axis starts to bend out. So this is why this thing looks a bit strange. Yeah? And then finally ends up in a circle. Yeah? And so you can now look at this from what is always useful if you get lost, think of the reflection. It's an overlay of putting reflection coefficients. Yeah? And the trick of this diagram is that in this diagram, when you're showing in the impedance relative to what you have in your hands, the reference impedance, you directly get the reflection coefficient. So let's make an example of what I said previously. So here we are at 50 ohms. I'm starting with a 50 ohm cable and I'm connecting it to a 100 ohms cable. So the 100 ohms are roughly here. So I know directly, because I'm transforming up, I get 0 phase and I get so and so much reflection. Very simple. Yeah? If I'm transforming down, I have a 50 ohm cable connecting it to a lower impedance cable, I will get a phase turnaround. Yeah? And this is consistent with this here, because here we have some impedance and the impedance goes down, whatever it is, but it goes down. Short circuit is a down. Yeah? And then you see in consistency, this is 180 in the phase. It's a very simple thing to remember. You don't need to know much. And here it's an open, it's an up transformation, maintains the phase. So that's what happens on this. And now we have to deal with any other occurrences. Yeah? And the question is now, what could be connected? And this is what we do here now. This is now the bit broader way of looking at this. So again, I plotted the reflection coefficient. And now things hit which you know. There are some things which you know already. For example, what is the impedance of an inductor? I omega L, yeah, that's very good. And which has a dramatic consequence that suddenly you have the frequency dependence of the wave in there because you have omega. Yeah? So we're starting with something which is real, and we're transforming into something you're connecting to an inductor with a certain L at a certain frequency. So you can now guess from the value which you somehow put in this diagram that what happens. Yeah? So let's assume we take a certain value now for the impedance, and an inductor has at 0 frequency has no impedance. It goes up, as you just told me. So the inductor goes along with frequency, goes up here from 0 to up here. So depending on the value of L and the frequency, you can now guess what happens if you're connecting a cable to an inductor. And the easy answer will be you will have, again, a total reflection, and the phase will be strongly frequency dependent. Yeah. So that's what we can read from this diagram relatively easy. So if the inductor is at 0 frequency, you have a relatively strong mismatch between 50 ohms and 0 ohms. Yeah. So that's what this is. But this is boring because there's no frequency information in. But you just told me the truth, which is the truth is that the impedance of an inductor is increasing with frequency. You knew that? What I'm telling you now is that it means that the reflection of the phase of the reflection goes down. So it's less than 180 degrees. And how much is determined by the frequency. And that is not so shabby, because 5 minutes before you wouldn't have been able to tell me something. But with this diagram, you can now say, okay, it is a total reflection because the real value is not changing, but the imaginary value is changing. And by how much is determined by L and the frequency. Same for the capacitance. What is the impedance of a capacitor?
1/J.
Mm-hmm. And in this case, it's easier to say minus J 1 over omega C, because then it's easier to determine the sign. Yeah? So that's why then it's a negative. And then as we said, for zero frequency, the capacitor has an impedance of infinity, and then depending on the frequency and the value of C, it is reducing in its imaginary value. Yeah? So the capacitor goes along here, depending on the frequency. Which is why the top half of the diagram is called the inductive area, the red one, or top inductive area, and the lower part, lower half, is called capacitive area. Why is this useful? What have we learned? I would say a lot. So for example, what you learn immediately, just as a very simple example, you have the input of maybe of a field effect transistor connected to a cable. Yeah? What can you tell me about what's going to happen? Yeah? So a FET at zero frequency is an open. So if you're trying to put something into a field effect transistor, you unfortunately get a total reflection at the input. So you have to think a little bit just to get the signal in. Yeah? Not so easy. Same. Another idea is to get the signal then out of the FET, depending how big it is. If it's very big, it has a very low output impedance, so it's somewhere here. So it means that getting the signal out of a field effect transistor is also not easy. So you have to do something. Yeah? And that's, if you would simply connect it to a 50 ohm cable, this would not be an amplifier. You have to think about something. Just as ideas why this might be useful. Let's do some exercise. So I was already referring to that. So this is the open. Sorry, this is the short. So this is the we are shortening the output. So we are here. So this is this. Yeah.
I never seen this picture before. I don't know how it is for the others. I don't really get where we have which numbers. So I got the idea of bending the grid somehow away from the x-axis, but where's now the 0?
Yeah, very good. We have that here. So this is the central, and when you, that's something good for asking. So this is the reflection. Yeah? And the question is what happens with the impedances. And what you're taking is normally the you have to, from the reflection, if you have an impedance of let's do it this way. So we are starting from putting the reflection coefficients in real numbers, real and imaginary numbers. This is this. Yeah. And now you're putting it into the into this diagram. The idea is that the impedances, when you turn around, you have the impedances here. You have a positive impedance and a negative impedance, minus infinity and plus infinity. Both not approachable, which, however, would contribute to this reflection coefficient of 0 and 1. And to get it consistently done is to think how to put that into a diagram that the numbers of the impedances which are of interest, which is infinity for the impedance, are showing, because normally in this there would be somewhere out of range. And now you're transforming them back into the diagram. So what you achieve is, that is the trick, that here you have an impedance value of infinity. Make sense? So this point before was somewhere, and it transforms back into here. And why is that? Because this is exactly this situation. So we move it close, and what this thing does is that from having the impedance, which would be far out, we're pulling it, and we're pulling it close so that it ends up here. A bit strange, but it's graphically it may be confusing. What you are doing is exactly this. This is this transformation. So the impedance, and this is the impedance is W, and it's even divided by a number, so it's general. Yeah, so, but this is this back and forth. So you're saying there's a reflection coefficient on a typically polar scale, and then you're plotting the impedances in a way to put it also into a diagram. And this is this back and forth. That is the easiest way to explain it. Yeah? And why? Because this situation conveys a very high impedance. Yeah, so that is why this value, if you plotted it, and you could normally plot the polar, but then you wouldn't know what the impedances are. But if it's in this transformation, and this is the overlay, so you put the polar diagram for the reflection coefficient, and the question is, you can put a Cartesian diagram underneath, but they have no relation. But if you do this transformation, you get a one-to-one between the value of the impedance and the polar diagram of the reflection. That is the idea. This is a double diagram, yeah, which is say, so the reflection coefficient relative to this reference impedance is directly one-to-one to the impedances which you see. This is the beauty. Yeah.
It's hard to grasp. It's hard to understand.
No, it's very simple. It's very simple because the reflection coefficient is just plotting polar, phase and magnitude. Which impedance is related to that, you don't know. But in case you transform the impedance in this way, and that is why the lines are bending, you can put on top of each other. So if you know this thing is reflecting, seen from an impedance, you directly know what the reflection coefficient is. If you see the reflection, you directly know what the impedance is, and vice versa, because this is equal. Yeah? And that's why the lines are bending. Yeah? How can you check that? The open port here would normally be somewhere not reachable. Because I have transformed infinity to this point, I know this is going to reflect with the total reflections of this here, phase 0. I know infinity is just here for the impedance. Same for the short. So I'm shortcutting it, yeah? And this normally would be a value of 0 for the impedance, so you could guess. So in this case, the impedance, let me go to this here. This would be normally somewhere here in the center, and this goes then here to this. Yeah? It's a nonlinear transformation, so it's a bit hard to describe, but it's a reflection of 0, and then on the other side you would have what is the impedance of it's impedance of 0, but still would be total reflection with a phase. So that's why 0 then ends up here. It's mathematical. I think that you shouldn't overstress it. You should consider why it's useful, and then it helps because you have these two cases. So this is the short, this is the open. Yeah, so these cases are included, very strongly non-linear. And the second thing is that is the easy way. If you match the same impedance to the same impedance, nothing happens. So no matter what the reference impedance was, if it's the same, you just continue the transmission. Yeah. And then you just take some cases. So for example, this is now the impedance of what you just told me, the inductor. And that would be also a short, yeah, because the inductor has no resistance at the frequency, and then this turns up depending on the value of L and the value of omega.
Can you draw the circuit for this example? So it's like these two lines, and between them there is an inductor, and that's why you have this Smith chart, or how should I understand it?
The first thing is that you include, that's interesting. The first thing is, what is the value for the impedance that you put?
Is it something like a reference value where I choose it, or is it something that are given by a certain technology or something?
No, just very simple. This is a diagram which says, so this diagram has impedance 0 at this point. Yeah? And then phase goes up. So this is just your setting point. So these are different impedances depending on the frequency. So these are, let's say these are, in this case, these are 5 inductors. So this is either the same inductor with an increasing frequency, fixed L, or you could, with a grain of salt, omitting the 0, you could say this is for the same frequency and increasing L. So you get real numbers for the impedance. This is what you plot there. And then in relation, that is the overlay, then in relation to the whatever you, for example, do in the center, if you are at the reference impedance, you directly also know what the reflection coefficient is. And we come to that. I didn't want to confuse you, but we can, if you ask it, we can directly go there. So for example, when you now look into something, yeah, so you're starting with a certain impedance and you look into something, what do you get? Yeah, so for example, let's take this. Yeah. So when you now connect, so for example, you can now plot various impedances in this diagram just values. Yeah, so it's very simple. Yeah. So for example, you have a 50 ohm impedance, and then along these circles you have all the impedances which have this constant real part. These are these circles. So this is maybe 50 ohm, and this is 50 ohm plus I something. Yeah? And all these impedances which have the 50 ohm, they go on this circle to the point that you're expanding the imaginary part to infinity, and then you're ending up here, in theory. Yeah? But for practical things, so for example, putting 50 ohms plus I 50 ohms, and how do I know this? Because there's typically also a annotation here that this is I 50 ohms. Yeah, so that's, and this would be then the lines here would have a higher value for the imaginary part, 100 ohms, 200 ohms, because how do I know this? Because this is the open part, and the ones which have a lower than 50 ohms, they are going here. So it's 50 ohms plus 20 plus I 25, and so on, that you're going down here. And the red lines are the ones with the constant imaginary part. Yeah, so you have the constant real parts. Yeah? So for example, everything which is on this circle has a real part of lower than 50 ohms, maybe 10 ohms in this case, and then this is plus 10 ohms plus I something, and this is 10 ohms minus plus I something. Yeah? And in relation to the reference impedance, you directly go to the other. And this is helpful because, for example, you for designing now connecting two structures, you could say, in order to connect, because nobody has asked that question, but let's assume I have a transistor. This is a field effect transistor. I just told you you don't get in. Yeah, so here's 50 ohms. I want to put a signal, and it has to go in here. We just learned it has an open behavior. So apparently I need something in between which transform the 50 ohms into something that I get the signal in. Because if I just connect 50 ohms to this, there would be no signal entering. And this is exactly what this complicated network does for me. And how do I construct this network? That I search for something, and that is the beauty of this thing, that I go along these lines in the transformations from here to here. Yeah? So I may go, let's say, with the first component, I go a little bit up here, then I walk along this line, and then I take a cross section down here, and then have another transformation. Yeah, so you can going along these lines implies that you can do transformations of through the Smith chart. Let me make an example where this is most visible. So for example here, that's what you ask. So you have, maybe you are here with your impedance. Yeah? And now the question is to go to here, how can I do this? So you choose a value for the serial L. So it's, first of all I have to know it's serial, but the longer, the higher the value of this L is, the higher you go in this. How do you know this? Because by increasing the L, you increase the imaginary part of this impedance. So you strengthen it, and if you want to go here, you can go up to this point. Yeah? So just as a simple example. Yeah? What do you get from this? You transform by using a component from one impedance to the other. Yeah? And you can ask now, why should I go from this value to another? You have combinations. Yeah? So essentially you would like to connect to 50 ohms because this is what you might want to transform to, yes. But you are here serial, but by adding another component, which then might walk along down here, or there's another trick to go down here, you can actually transform through the Smith chart. So for example, let me take a very simple one, which we are always using. So for example, the serial resistor, very simple, will have a constant, whatever it is before, will have a constant imaginary part, but a change of the resistance of the real part. Yeah, so you go with a constant imaginary part, you go along, depending on the value of R, you go to a higher value, which in the serial case is very easy to understand because you just add real part. Yeah? So with whatever it is, you're transforming down here. Yeah? And for example, just with the previous one, maybe you are here, then you're transforming down here with a bit of resistance, and then you're going down here with a bit of capacitance. And then you go from A to B, applying elements. This is the idea what we just learned. Yeah? So this is a relatively simple way of understanding what these components are doing for you. Yeah? So you just got kind of a recipe. So we have this idea, there's a cable and a component, you want at a certain frequency to match them, you start somewhere, and then you're just intelligently assuming that these lines are constant in something and varying in the other part. So in this case, this is constant real part and varying in the imaginary part. You just add components which do the specific transformation, and you even get the value because you know how far it goes. Yeah. So going from here to here could be going up here, going down here, turning down here with a capacitor. Yeah. let's talk. This is the serial L, series C, yeah? And let me also show you some which are more. I think I have the capacitor also somewhere. Capacitive would be, it's very simple. Capacitive would be, not to say something wrong, the capacitor turns along these circles here, if it's starting here, and if it has not an infinitely high value, you're going always along these circles here. This is the inductive thing. Sorry, this is the capacitive one, and this is the inductive. Yeah, so you're adding either, or you're going down. I hope this becomes clear. And this is serial R. That's easier to understand because there you have a constant imaginary part changing real part going down, and then whereas somehow the capacitance has not shown. So the inductor is always turning up and the capacitor is always going down. Now, why are we not looking at a serial capacitor here? That is a bit strange, and that is why I don't have it in. Not to confuse you, but there is actually a triple diagram, and because this is serial L. What about the parallel L? How could you see that? And this is easy. Going back. You turn it around. That's what I was searching. So when you can look at this diagram from the impedance part in this impedance region, and you can also turn it around. Why on earth would I do that? It's already complicated. Why make it even more complicated? And the answer is because I'm lazy. Yeah. Because what you can say then is you can, for example, in capacitors in series are adding. Sorry, resistances in series are adding. R1 plus R2 makes R. Capacitors, the impedance of a capacitor is 1 over C, 1 plus 1 over C2, if they're in parallel. It's 1 over the total capacitance. This is not nice. But for a capacitor, you can turn it around. You can look at the admittance. Then the admittance of a capacitor plus the admittance of the second capacitor is the admittance of the total capacitor. So you do the same thing. So instead of starting crazy calculations, you just flip the diagram, yeah, and then you know capacitor in parallel turns this way. Yeah, so that's why I didn't answer your question with the capacitor in the first place. So as long as you are in the impedance diagram, expressing L is very simple. Goes up. That's what we are doing here. Yeah? Changing resistances is very simple. Why is that? Because the impedance of inductors and resistors, when you add them, add to the total inductance and also to the total resistance. Yeah? Capacitors is inverse, so that's why we don't treat them in this diagram. We go to this diagram where we turn it around, and then we are adding the admittances of the capacitor. So you just go along these lines. You just turn it around, and then you look at the admittance, and then you just change the admittance accordingly. You are here at this point, and then you turn it around, and then you know that the parallel situation is much easier to be dealt with. Yeah, so that's why I couldn't explain it in this diagram, because here the impedances are shown, so the lines are forming up. If I look at the same diagram from the admittance, coming, let's say I have what I just said earlier. So I'm here, I've transformed here, and now I want to go down here. Yeah. How do I see this in this diagram? In this diagram you don't see, but you can just take the overlay and look at the admittance. So you take a parallel C and adjust, and then you to the point that you are transforming the reflection coefficient to here. Yeah? So, for example, when you want to transform from here to here, you could, for example, increase a serial L, have a parallel C down to here, and then make another transformation, just real transformation from higher to lower. Yeah? And of course, there are multiple ways to go there. You can of course directly also try to do that directly, but that's design. And what would guide you then, just to explain why there are multiple cases, the trick is then which components are possible, because here you're assuming you can find a series L, and whatever it is, you just put it. Yeah? But then you would say, I need a relatively large L, because we are increasing the L. Then you say, too big. Yeah? So maybe do I find another way to go here? And that's why these diagrams are getting useful, because already also the parallel C that you would need to go from here, and then the real transformation from high to low, or to lower, that wouldn't be appropriate. That's, at the end of the day, you can try and simulate, or at some point it's experience. Yeah? So for example, you would know at some point that this impedance that this serial value you need is too high. Yeah? It is just a visualization. Yeah? And it was used when people didn't have a computer to do it. But it's quite helpful, because you can say, okay, these transformations are critical. Yeah? And maybe also to just show you why we would be doing this here. So for example, here's now the series C, which would go down there. This is the wrong turn, yeah, so this wouldn't have helped us in this case. This is the series C capacitive matching, yeah. This is the serial R, and this is the serial L, yeah. So in this case, we are always in the same diagram, but as you see, we are not getting really from some interesting values to some others. So that's why this change in the diagram is useful, that you just then start to go parallel. So you combine a serial matching with a parallel matching in order to have something going up like that and then going up like that. And then you start to understand you can essentially go from everywhere to everywhere. Yeah? Because it's not only serial that you can apply things, you can also go parallel. And this third diagram, which I was showing you, is just because there's no preference for impedances. Admittances is the same, and think it from the idea of laziness. You were always in an exam quite annoyed if the teacher chose an example where you do 1 over C is 1 over C1 plus 1 over C2. Then you're starting to look, that's impedance. But if you go with the admittance, you just add the numbers. And this is the same as going along these lines seen from the other direction. Yeah, so it's just a triple diagram then. Yeah, so you see that the admittance diagram is just the red one is the impedance and the green is the admittance, and they just mirror over the real axis is the same, and you just have the other circles. Yeah. I'm honest, when I saw this first, I thought you are crazy, but it has some benefits because you can put the whole world into a circle. Whatever happens, it happens inside this diagram. And if you get, so it's a bit of a step, but it's a very powerful tooling. Yeah? And what you just learned, for example, is you can now with 2 components can go from A to B in the rest of the world. So you can essentially solve any problem which you have to solve to build something. Maybe this is a bit of a of a reward for listening to that. Yeah? What I'm trying to tell you is get away from a specific preference. I only do things in impedance. Don't do that. Think if you're lazy, It's like the internet. It's stupid in the beginning to use a camera to watch the coffee machine to invent the internet, but once you have the internet, you just look at the coffee machine and get the camera image. Yeah, so it's why invent the internet? Yeah, because it's simpler. Yeah, so and with this remark, this is the famous story from Bell Labs why they told the internet was invented, but maybe get a coffee now, think about it, and it's just procedures. It's making your life a little bit easier. And there's more. This diagram can do more than what I just explained. Yeah, but it is the principal action of being exposed to very critical states. What you do about it, it's one solution which might help you. So, and once you get to the arithmetic, it's fine. Because at the end of the day, we can put the behavior of a full fat over frequency in this diagram. So you get everything in one diagram. This I have to match this way. This is the amplification. This is what this thing promises at some point. Yeah. And again, if I was in your situation, the first time I saw this, I said, but then I got to it because it's convincing. Yeah. I will re-explain next time. Maybe you follow me, and then maybe there's some beauty. You start seeing some beauty in it, and it's just like. So now have a coffee and a good afternoon to you. Thank you very much.